So I'm Vamsi. So these notes will be put up on my webpage as well as hopefully on the conference webpage. And we are done. So my webpage, just in case, is this. All right. So you will be seeing my face for the morning the next 3 days. And I'm going to talk about, broadly speaking, complex geometry. With a view towards Kodaira and Embedding theorem. Time permits, I'll also do some generalities on vector bundles, which really doesn't have anything to do with this, but I believe Sushmita will talk about Young-Mills theory, so in general it's a good idea to know about vector bundles. But all of this is just the sponsor line, so to say. We might actually deviate heavily from the syllabus depending on your background. So in light of the fact that you need to get something out of this workshop, I strongly encourage you to ask questions or tell me to slow down and so on and so forth. Please remember, there are no dumb questions, there are only dumb answers, namely the ones I will give you. So before we start, maybe I'll write a few words on the board and you can tell me if you know these things or don't know them so that I can get an idea, maybe. Okay. I hope these words are familiar to you. This I do not know. These two I'm almost assuming surely not. Do people know what this is? How many people know what this is? Can you raise your hands? Okay. What about a vector bundle? Right. Theorem cohomology. People who don't know these things, anyone? Please feel free to raise your hand. Okay. What about this? Just these three? The first one. The first two you know, but the others. Alright, let's see. No problem. So, okay, at least all of us know these. Just one more phrase. Do people know this one? Okay, wonderful. Also, I have a nasty habit of erasing things as soon as I write them. So just if you catch me doing that, please feel free to tell me off. Okay. So we all know what manifolds are. So what is the aim of studying manifolds? I mean, what's the aim of differential topology, so to say? The aim of the study of manifolds, so-called differential topology, is to write a list of standard manifolds such that every manifold is diffeomorphic to one of these. This is the aim, right? This is the classification problem, so to say. Right? Now, what is the meaning of write a list and so on? These are more technical topics. And this problem, as stated, cannot even be solved. Provably, you can prove that at least for dimension equals 4, this can't be solved. Okay? So already it's a very ambitious program, right? And it's not just restricted to differential topology. I know some of you probably don't know what this is. But for those who do, well, you can have similar programs in other categories. In Riemannian geometry, you're given a manifold and a metric, which is just a way to measure distances and angles. And the aim is to write a standard list of manifolds with metric, so that every manifold is isometric to one of these. Okay? And you can keep going on. Whatever object you can define, that is the aim of that subject. Right? But since it is too hard, let's try to make it a little less ambitious. In fact, very, very less ambitious question is this. Is every manifold secretly a submanifold of some standard one? This is a much, much easier question, and the answer is known completely, right? So this is the statement of the Whitney embedding theorem, that indeed the answer is yes. Whenever I say manifold, I don't know what you people define it, but it's Hausdorff and second countable. Okay? You can drop the second countable assumption in certain cases, but we will always pretend that that's the case. Rn for some large n. Okay? Likewise, even in Riemannian geometry, in Rn there is a metric. There's a way to measure distances and angles, and every Riemannian metric actually secretly comes from there. In other words, if you take any manifold and any metric, you can isometrically embed it in some Rn. Okay? So this is the Nash embedding theorem, akin to Whitney. Nash embedding. Now, the topic we will study is complex geometry, which involves the so-called complex manifolds, which I will define. And as before, one can phrase these questions. You can also phrase this question. Surprisingly enough, the answer to this question is extremely complicated, at least given your background. Okay? Even phrasing this question is non-trivial. What standard one can you choose? Rn, right? Obviously. Here that doesn't work. So what can you choose? That itself is not straightforward. What is the model manifold? And even if you choose the correct one, you can't embed everything in that. Okay? So a partial answer to this question, is provided by the so-called Kodaira embedding theorem. But before we even go to that, I hope people know why you care about manifolds and submanifolds. It's not just enough to know definitions, theorems, and proofs in mathematics. You need to know why to care about them. Assuming you know that, and assuming you know why to care about Riemannian manifolds, I can of course define complex manifolds, but I'll tell you why to care about them first. It's not just to generalize. That's a stupid way of doing mathematics. So let's start with. Before that, actually, even before we go to complex manifolds, let's go over a very brief proof, rather at least over the ideas of the proof of the Whitney embedding theorem. Have people seen the proof of this theorem, by the way? How many have not seen the proof of Whitney? Okay. But you guys know the statement. Okay. So how would you hope to put something in Rn? What would that even mean? It would mean that I need to, so by the way, just one more small pedantic point, and that point is this. So when you define manifolds, a manifold is a union of open sets, each of which is homeomorphic to Rn. Right. Okay, maybe an open set in Rn if you prefer, by means of some phi alpha, right? And for a smooth manifold, this is a diffeomorphism, right? This is the definition. But owing to my physics background, I'm going to pretend that whenever you say U alpha, you're already sitting in Rn. In particular, I will never write these. Okay? Right. So when I have local coordinates, I'm already sitting in Rn. Okay. Alright, coming back to this, what does it mean? Let me put a vector here just to indicate it's a vector valued function. It means I have a collection of n functions, and such that this is one-to-one, of course, and it is an immersion one-to-one. So it's a homeomorphism to its image. Some of these conditions are redundant, but might as well. It's an immersion. Do people know what an immersion is? Immersion is a very fancy term. It just means that if you take local coordinates locally on U alpha, you have coordinates, right? x1, x2, so on until xn. This matrix has full rank. That's what immersion means, right? In other words, no vector goes to 0, right? The derivative is one-to-one, so to say. And this doesn't depend on coordinate changes, of course. So you want to produce something like this. Now it seems a little hard, right? How do you produce a function on a manifold in the first place, a non-trivial function? Forget about the one satisfying your properties. Here is where a very important tool, the so-called partition of unity, comes into play. A partition of unity, subordinate to an open cover, is simply a collection of functions, rho alpha from M to R. They have compact support, and their sum equals 1. Okay. So what you can do is the following. You can have a map from U alpha to Rn, of course, given by a point goes to its coordinates, right? Let me put an alpha here, sorry, I'm using superscripts. X alpha right? So this is something that puts U alpha inside Rn. Well, how can I make it a global function? Meaning, how can I define it over all of M? Here is a function to Rn, namely, well, P goes to rho alpha x alpha 1 of p, rho alpha of p, rho alpha of px2 and so on. So we have one function from M to Rn, except that this guy is 0 outside an open set, which is not what we want. You can modify it instead into some large n by taking the others. Maybe rho alpha 1, rho alpha 2, and so on. Namely, use all these coordinate charts to produce such functions. This more or less does the job, roughly speaking. Okay? So in other words, what is the basic strategy? You produce local functions which come from the definition itself, and you have a machine, the so-called partition of unity, which allows you to globalize local things, right? This works for compact manifolds. Why? What's wrong otherwise? Yeah, you'll have infinitely many, right? Potentially. You can make it work for non-compact ones, but that requires more effort. Okay?
So this is basically a weaker version of
Yeah, it's a weaker version.
Because you're embedding in some n.
Yeah, for compact ones. It's weaker in many senses. It's for compact ones, and you're right. This n, technically, by the way, since he has mentioned it, you can bring it down to 2n plus 2. Even lower, but at least this much. Okay? The lower thing requires a little more effort. Anyway, the bottom line here is what is doing all this magic is the so-called partition of unity, and this has compact support. You will see why I'm being so fussy about it in a moment. Okay? Okay, let me actually give away the suspense. Why am I being so fussy about it? If you have a holomorphic function, so by the way, I'm assuming, of course, everyone knows complex analysis in one variable. This is a hard prerequisite. Okay? Can't get away with that. So if you have a holomorphic function, can it have compact support? Right, why not? Sorry? Right, that is fine. The point is, I was looking for another word, the identity theorem, because I will need this phrase later on. If a holomorphic function is 0 on an open set, on that connected component, it is 0. Okay? Okay. So automatically we can see whatever complex manifolds are, we have not defined, but surely they will involve complex analysis, and these sorts of tricks won't work. Okay? So already we can see things are going to get very hairy soon. All right. So what's next? Okay. I will first give a tentative definition. This actually is the full definition, but you don't know the meaning of some of these phrases. A complex manifold of complex dimension, let's call this, I think I'm calling it M, dimension n, is a smooth manifold of dimension 2n such that there is an open cover where this is thought of as sitting in Cn as opposed to R2n. Phi homeomorphic to an open set here, inverse is a biholomorphism. This is the word that you don't know yet. You think you do, but you don't, because n can be larger than 1. First, why did I say R in it? Cn. N can be larger than 1. Okay, so what does it, so first of all, firstly, what does it mean for, if you have a biholomorphism from C to C, that means F is holomorphic or it is analytic, whatever words you want to use, and F inverse is also so, right? For what does a holomorphic map even mean? What does this even mean? Right? We have to first define that. That's the topic of several complex variables, more than one complex variable, and it holds many surprises. Okay? So this is the definition, sure, but we have to do a lot more work for us to even make sense of this definition. The first and most important thing is, why the hell do we even bother? What's the point of defining this? And the point is as follows. So in high school, what does geometry deal with? So high school coordinate geometry. I mean, this was geometry due to Descartes, and even earlier, many of these theorems were proven by Greeks and other ancient civilizations, right? It deals with what? Things like this, right? Straight lines in the plane in R2, like y equals mx plus c, and circles, and other conic sections, this one and this one, and so on and so forth, right? So you deal with these, and what kind of questions do you answer? How many lines, let's say, a stupid question is pass through 2 points, and whatever, how many points do you need for defining a hyperbola, and so on and so forth. If you have two hyperbolae, how many points do they intersect in? These are all questions that we deal with at a very elementary level, right? And they follow by just using some basic manipulations. At most, you will have to, if I give you like ax squared plus bxy plus cy squared and so on equals d or something, at most you will have to complete squares. Basic algebra tricks do the job, right? But the problem is, so more generally, you can ask this, not for just what is so special about circles, and this is a degree 1 polynomial, this is degree 2, right? There's nothing so special about these. It's not unnatural to ask these questions for higher degrees. In fact, Newton did for cubics, for example. So more generally, you can set a bunch of polynomials to 0, f2, etc., where fi's are polynomials and xi's are real numbers. This is the most obvious question to ask, right? Any mathematically interested person should be interested in this sort of a thing. But the problem with these questions is, these are very not just complicated, but complicated for a very precise reason. Namely, you see, real numbers are a pain in the neck. X squared plus y squared equals 1 is a circle, whereas x squared plus y squared equals minus 1 is just a joke. It's not anything, right? So that's the problem. You have to keep track of signs and so on, which is not very algebra, right? In algebra, you don't have inequalities, you have equalities. So what's one way to fix it is to pretend, so what is the most natural thing in life? It is real algebraic geometry. This subject is called real algebraic geometry. Shockingly enough, it's not developed as much, and there are very few people working on this. What is more natural from a mathematician's standpoint is are complex numbers. Then things get more interesting. Okay, because if you've done algebra, I mean, for starters, you have the fundamental theorem of algebra, x squared plus y squared equals -1 still makes sense. And more sophisticated tools like the Nullstellensatz and so on, all those fancy words can play a role, right? So given that we think that these sorts of things make sense in Cn, setting a bunch of polynomials to 0 and studying what happens, well, it is obvious now as to what to do. Well, how do you come up with examples of smooth manifolds, firstly? Here is a silly question. How to come up with examples of smooth manifolds? Well, you just set a bunch of functions to 0, for example, right? So automatically, whatever these things should be examples of complex manifolds. We don't know that yet, but it's reasonable to expect that. Okay? So that is the reason to care about complex geometry, complex manifolds, because we have natural examples of these things. And indeed, as we progress, you will see that complex geometry, the study of complex manifolds, is related to, so complex geometry has several facets. It has to do with algebraic geometry, which is the main point. It also gives rise to very interesting examples in Riemannian and symplectic geometry. Even if these words don't make sense, not to worry. Geometry, right? In a sense, it also has to do with number theory. There is something called Archilov geometry. And of course to complex analysis and to PDE, as well as physics. So it is a very vast subject. There are lots of problems, obviously, coming from various sources. In fact, there are certain results in algebraic geometry that you can state using just algebra alone, using polynomials alone, if you will. But to prove them, you need PDE theory and complex analysis. And vice versa. There is a question in Riemannian geometry that you can state using metrics alone, and its proof requires, not just Riemannian geometry and some topology. Its proof requires characteristic P algebraic geometry, finite fields. Okay. So these things they are very heavily interlinked. Okay. All right. So before we go on to this once again, let's do something straightforward. Okay. So I'm still contemplating about these exercises. One model is to give you an exercise and make you do it here, and the other is to perhaps give you some time and ask you tomorrow. We'll probably do both, but this is so straightforward, if you wish, that maybe we can do it here. Apologies to the experts if this is boring, but So is this a submanifold? A smooth, forget about complex geometry. If so, how do you prove it? There is a point to asking this question. Sorry. Yeah. These are complex numbers. There is a point to asking this question. How do you prove that this is a submanifold? Yes.
R2, how we do it, the inverse image of F inverse 1, and then at 1 it is surjective. That will not work.
So what he is saying, which is an important point, is how do you prove that this is equal to 1 is a submanifold in R2? Because this you can do it directly, right? You can exhibit coordinate charts. But the correct way to do it is to say that the gradient of this is not 0, 0 on this. So by the implicit function theorem, locally you can solve for one of these, for one variable, in terms of the other. Right? Therefore it's a manifold. The problem with, so what's the problem with applying that here? What is missing? We have not proven an implicit function theorem for complex things. You can still do this. Yes, potentially you can say that this is a function from C2 to, from R4 to R, and in fact this is R4 to R2, and you can try to do that, which is correct, but that's an overkill. Ideally you would need some sort of complex analog of the implicit function theorem, which we will get to in a moment. But there is a more elementary way of doing it, and there's a point in saying that. So what's a quick elementary way of doing this? Well, what's an elementary way of doing it in R2, for example? How do you prove that the circle is a manifold without using fancy words like the implicit function theorem? Sorry?
Pre-image
Is
theorem.
it zero set of
I mean,
polynomials?
x square plus y square minus 1 equals to 0, and that see that the surjective it is.
No. That is the implicit function theorem. I'm just saying more elementary.
You can parameterize this.
Okay. Well, you can choose an open set. You can actually give coordinate charts, right? One way is to parameterize, another way is to whatever. You can locally explicitly solve this, and depending on the region, you can do this, right? And you can try doing the same thing in C2 also, except it's going to be a little hairy because complex square roots are a pain in the neck, if not elsewhere. So that's the problem. So complex square roots are a pain in the neck, but the bottom line is the following. If you try doing such a thing, the transition functions are bi-holomorphisms. I leave this to you to check, to do it explicitly. However, this is not what I was looking for. The simpler point here is it's actually very straightforward. So you can solve for one in terms of the other. This is secretly just a copy of C star if you wish. You can actually solve for one in terms of the other because these are complex numbers, right? Right. So that is the point. That notice that already you can see whatever this object is, it's non-compact, and it behaves very differently from its corresponding cousin in R2. In fact, if you write any conic section, you can diagonalize it and bring it to a standard form, as opposed to R2 where you have a circle, ellipse, hyperbola, and so on and so forth, right? Okay, so already we can see a very big difference between our real cousins and complex ones. Okay, and this is the first example of a complex manifold of dimension 1. So from now on, complex manifolds of dimension 1 will be given a different name. They are called Riemann surfaces. They were discovered by Riemann in a somewhat analogous but slightly different context. Okay. And Shivojoy, my colleague from my IISc, will deal with Riemann surfaces in more detail. Okay. Okay. So I was saying that, alright, I erased it. Here I used the word biholomorphism between open subsets of Cn. So firstly, what is the meaning, definition? A function is called holomorphic. Well, what is a reasonable way to define this? Any guesses? How can we hope to define a holomorphic function of more than one variable? Sorry?
By fixing n minus 1.
Excellent. So one possible way is the following. F of Z1 to Zn is holomorphic separately in each of the Zi's. Any other way?
Multinomial expansion.
Sorry?
Some multinomial expansion, multivariable.
Okay. Locally, F is some C alpha, maybe Ci1, In, Z1 minus A1 raised to I1, and so on. Locally, right? So these two definitions seem to be reasonable. And any other definition, well, I said it's holomorphic separately. Maybe I can probably add this plus f is C1. Notice that in usual multivariable calculus of real numbers, just because a function is differentiable separately, the partial derivatives exist, will not even guarantee it to be continuous. Forget about being differentiable. Right? That's not really a great condition to have. But surprisingly enough, these are all equivalent. Any reasonable well, let me write another definition, for which this will be more important to us soon. So if you have a usual honest single variable function, f is holomorphic if and only if it is C1 and satisfies the so-called Cauchy-Riemann equations. Ux is Vy, Uy is minus Vx. But this is not a very great way of writing these. A better way is saying this. This fancy symbol just means this. Half this is exactly the same as the Cauchy-Riemann equations. You're just writing both of them in one shot. Okay, by saying del bar f is 0. This thing is, maybe I'll refer to this thing more than once. This is sometimes called the d bar of equation, or sometimes the Cauchy-Riemann operator. All sorts of fancy names. Okay. So f is holomorphic if it's C1 and so on. So you can also say that f is C1, and which is the same as saying what this means in this context is what is d bar f? Well, what I mean is By the way, this is also, d bar is also written as d dz bar. D dz bar 1 of f is 0, d dz bar of 2 is 0. It's just another way of saying it's holomorphic in each of these separately. Okay? All of these are equivalent. And the fact that they're equivalent is a very non-trivial theorem. It's called, so this chap Hartog did a lot of work in this subject, and there are several things called Hartog's theorems. This is one of them. The fact that these are all equivalent. But the proof is it's one of a kind, in the sense that it's completely useless after this theorem. So it's best to just know that any reasonable way of defining holomorphic in several complex variables works. All right. Okay, so since this is the case, also of course, yeah, this should do. Don't have to.
Excuse me, sir.
Yes.
In one variable, we don't need it to be C1 exactly. Means we can have just partial derivative existence.
Yeah.
Yes, here it is. So can we do
Yeah,
same
of course,
thing
of
here
course,
as well?
of course. Yeah. I don't need this. As I said, any reasonable thing you can do works. You don't even need it to be C1s. You're right, only partial derivatives exist. In fact, this is even better. How many here have heard of the word distribution? Not many. Alright. Maybe Dirac delta? Anyone? Physics. Okay. Alright, fine, no problem. You need it to be just L2 if you wish, L1 low. So it's very, yeah, it's very robust. Any definition would work, reasonable definitions. Okay. All right, so, yeah. So several complex variables, namely the study of these, is a very strange subject. For example, here's a very straightforward example. If you take f of z equals 1 over z, on C, this has a singularity at a point. On C2, namely if you choose coordinates z and w, it has a singularity on a huge set, not just a point. It's a whole plane filled with singularities, right? This might seem like a very, an example that I've just cooked up, but this is actually a very general phenomenon. And this phenomenon at a very deep level is what ties complex geometry to algebraic geometry. This is the deep fact that plays a role in all of complex manifolds without us realizing it. So this is called Hartogs phenomenon as opposed to his theorem. So the phenomenon is as follows. If f from Cn minus mod Zi is less than or equal to R for all I, is holomorphic, then something shocking happens. Then R is greater than or equal to 0. Yes, you're right. That is crucial. Thank you. Then it extends holomorphically, uniquely in a holomorphic manner to all of C. Notice this is a shocking result. What it is saying is, suppose R is 0, if you have a holomorphic function that makes sense on Cn minus a point, it makes sense everywhere. And this happens only in higher dimensions. In one dimension, this is clearly false. 1 by z shows you, right? And this is the deepest fact, in my opinion, in several complex variables, because you will see later on, just to give away the suspense, if these words make sense to some of you, otherwise ignore it, that sections of the O1 bundle are polynomials follows from this. And that is what underlies most of algebraic geometry, the relation between algebraic and complex geometry. Nonetheless, so let's see why this is the case. Proof in the sketch of proof for n is equal to 2. Let's say we have z and w. So f of z and w. Okay? And it makes sense on C2 minus mod z is less than r, mod w is less than r. To C, sorry. To C. Okay? So let us draw a picture of it. Well, how does one draw a picture of 4 dimensions? One doesn't. What one does is something else. You take mod z, if you throw out it makes sense here, and does it make sense here is the question. Okay, this is R. Okay, we somehow have to make sense of this. Well, how can we make sense of this thing? Here's one way. Suppose you take R plus 1. Okay? Take a point here. Honestly speaking, fix W, did I fix W or Z? Fixed the other one. Fix Z, consider, fix Z and consider this is, okay, I should be drawing this in more than these many dimensions. Consider W equals R plus 1, a circle in a fixed plane. I hope, yes?
Do you mean greater than equal to R in the statement?
Where is that?
Mod Zi greater than?
No, C2
No,
minus.
no, above that. The function, definition of the function.
Here?
Yes.
It's minus. I'm
Okay,
throwing
sorry,
out the
sorry.
small part. No problem. Right. So, where was I? So, I hope this is clear. What I'm doing right now is I'm fixing the z coordinate. I'm letting the w coordinate vary in a circle of radius r plus 1. Okay, maybe you should think of it as maybe a circle like this, whatever. Well, why am I doing this strange thing? What I want to do is the following. So if I want to define my function here, right? Like let's say I want to define it on z1, z. This is a horrible picture I've drawn, but the aim is to define f of z1, z2, where z1, z2 is in the forbidden region. Okay? So how does one do it? What one does is use this Cauchy theorem. Integral of mod w equals r plus 1 f of what did I call z comma w. So z comma w Z1 comma W. I hope the definition makes sense. What I'm doing is the following. I'm just using the Cauchy integral formula to make, I'm integrating over a circle and this point is inside the circle, if you wish. Right? This plane is to be thought of, it's a circle like this and a point inside. And I claim this solves the problem. Okay? This should automatically raise suspicion in your head. What prevented me from doing the same thing in one dimension? Okay. So what goes wrong for n equals 1? Okay, first of all, this is holomorphic. That is true even for n equals 1. That is not the problem. In Z1 and Z2. How would you prove it is holomorphic, by the way? How would you prove this sort of a thing is holomorphic? Well, one strategy is to probably try making it satisfy the Cauchy-Riemann equations, right? But that would involve taking a derivative inside the integral sign.
You could expand it in Taylor.
Excellent. So, as he was saying, you can try expanding it in a Taylor series, although the correct phrase here is a Laurent series, but you're right. How can you expand it? Well, it's a geometric series, right? 1 over 1 minus x, right? So you can write a Laurent series and directly see that it is an honest-to-God holomorphic function, right? That is not the problem. That works here as well. We have not done something yet. We have not completed the proof of this theorem. And that part doesn't work there. What have we not proven yet? We have proven that f is holomorphic. That seems to do the job, right? We've defined the function here as well.
If it agrees on the boundary.
Excellent. The point is, this thing, how do we know it's an extension of the thing we had? Right? You can see this thing. What if Z1, Z2 is not in the forbidden region? Then how do you know it gives you the correct thing, right? That is something we have to check, and that does this extend? Does it agree with, rather, our function? The answer is no here, but yes in higher dimensions. The crucial point, why does it work in higher dimensions? Because if your Z1, the guy you're fixing, if it was here, this is just the usual Cauchy-Riemann formula, right? The Cauchy integral formula directly tells you that this is true if you are outside the forbidden region, if Z1, Z2 is in the domain. It's just the usual one. Why does it fail in one dimension? Because the Cauchy integral formula works only on simply connected regions. Okay? So that is the point. You're giving yourself more room by moving up in a dimension if you have more than one dimension. Okay? Well, an algebraist would say it slightly differently. If R is equal to 0 as opposed to strictly positive, holomorphic functions can have problems, can have singularities on codimension 1 or below. Complex codimension 1 or below, but a point is not a complex codimension 1. But that's okay. Just ignore that comment. I hope this proof is clear, right? You're giving yourself more room to extend.
So, Vamsi, are there examples of, say, compact, simply connected things where Hartog does not hold? I mean, is there some other convexity also which is involved in this?
There are examples. I could be wrong, but something like this fails. Yeah, there are examples. Usually you're supposed to have pseudo-convex. So let's come back to this. If f of z1 no, actually, I take back what I said. I was thinking of a different situation. Yeah, you're right. If C is compact, C minus K is, I think, simply connected. This works. So anyway, if f of z1, where this is a holomorphic function on, let's say, all of Cn, before going there, just one thing before I forget. You remember in this case of smooth manifolds, for smooth manifolds, sorry, I'll just erase this definition because this is not the definition. I've kept erasing stuff. In smooth manifolds, we sometimes say that this is homeomorphic to an open set in Rn. Some people would directly say this is all of Rn itself. But both of these are equivalent. Why? Because if you choose a small ball, it's diffeomorphic. If it's open, it's diffeomorphic to all of them. But in C, in complex numbers, that's not true. I mean, even in one variable you can see, right? The unit disk and all of the complex plane. And one more, in fact, even something stronger holds. The Riemann mapping theorem is false in higher dimensions. In other words, if you take, let's say, the unit disk cross the unit disk or the unit ball, maybe I call this B1. These two are different. They are not biholomorphic to one another. It's not a trivial proof, by the way. It's a very non-trivial proof. So biholomorphisms of domains is a very big subject in several complex variables in its own right. Okay? So you are not supposed to say, get rid of this. It's always, in the case of complex geometry, an open set. Okay. So suppose this is holomorphic. When is this a submanifold of Cn? So what does a complex submanifold mean? It's just what you think it is, namely, well, one way is that the inclusion map from X into Cn, this is a holomorphic map, and it is an immersion in the smooth sense. That's good. And it's a smooth submanifold such that the inclusion is holomorphic. It's a complex manifold in its own right. It's a smooth submanifold. The inclusion map has to be holomorphic. Whatever you think is the definition, everywhere you have a definition in smooth manifolds, just throw the smooth out and put holomorphic there. Okay, that will work. So that's why I didn't bother defining what this word means. Okay? So, what I mean is there an implicit function theory? Function theory. What should it mean? Ideally, this should be true if when restricted to f equals 0. What do these mean? These mean the usual complex derivative. I mean, if you wish, this is limit as h goes to 0 f of z1 plus h, f of z1 over h, or alternatively, this is half of d dx plus, sorry, there, the other one, d bar, sorry, I'll just, let me just correct myself, plus, the other one is this. Okay, so okay, so ideally this should be the case. In reality also this is true, thanks to a complex version of the inverse function theorem. Using these, has everyone heard of implicit and inverse function theorems? Hope so. Alright. So the point here is that this follows from a complex version of the inverse function theorem. Okay. So what does that state? If f, I'll write a vector value function for the sake of clarity, is holomorphic and this matrix df. By the way, being a differential geometer, I have this nasty habit of writing subscripts and superscripts and exchanging them whenever I feel like. Please don't get confused. If you do, I'll actually might as well just use subscripts. The determinant of this matrix is non-zero at a point P. Then locally around P, F is biholomorphic to its image. Locally. In other words, locally there is an inverse for this. You can solve for one of these, and you can solve for given this in terms of that. Okay? Actually, this is an exercise. Prove this. I'll give you, you can do it, perhaps we'll discuss it tomorrow or maybe the next class, but prove this. You might think that it's very complicated because to prove the original inverse function theorem is a very big pain in the neck, right? Do you guys remember it? Because I don't. That's not what you need here, that's the point. Okay? You need, let me give you a hint, it is just the usual inverse function theorem can be used to do this. Okay? Okay. So we will pretend that we will just assume this to be the case and go on. Here is where I'm going to assume that you know differential forms. If you don't, maybe you can come and discuss with me later on. Okay. Riemannian metric, I can still go over these two things a little bit, but this, let's see. So, just as we have the usual differential forms in Rn, like say x1 dx2 or e raised to x1 x2 dx1 wedge dx2, etc. Well, unfortunately, you're supposed to know what differential forms are, but we can discuss it later on. You can come to me, I'll just give you a crash course on it. These things. Just like we have these, in complex, we have two kinds. We have, say, z1 dz2 or z1 dz2 bar, z1 dz1 wedge dz2 bar, wedge dz3 bar, etc. Or can, not necessarily that this is holomorphic, it can be, let's say, e raised to mod z1, z2, z2 squared, z1 bar, z2 bar, and so on. I hope at least these sorts of examples are familiar to you guys, if you know differential forms, that is. In complex, well, what do these things mean really? That is what should be puzzling to you. dz1 is just a fancy way of writing this. dz1 bar is of course this. So secretly, we are just taking our usual differential forms and we are allowing ourselves the ability to add them with complex numbers. We're making it into a complex vector space, if you so will. Okay? But by the way, you already see why I chose this convention, right? That I erased. If I take this, why did I put a half here? Because dz1 is 1, right? If you don't know what differential forms are, they are things that take in vectors and spit out numbers, basically. Right? If you wish, they are infinitesimals in the language of Newton. Infinitesimals. Like, remember in calculus, you write something like this for integration. Well, these are on, actually speaking, differential forms. Alright, so the reason I'm making a fuss about these, this is called a 1-0 form. This is called a 0-1 form. This is called a 1-2 form. And so on. You see the pattern here? When I say a PQ form, what I mean is I have P of these things and Q of the other chaps. Alright? So these are the so-called PQ forms on Cn. And these coefficients can be arbitrary, okay? They don't have to be even continuous functions. I mean, then I'll say continuous differential forms, or smooth, or so on. Okay? Let's just keep this. Erase this. We have more to do with differential forms, just in case you thought you got off the hook. Okay. So, in Rn, suppose eta is, let's say, for example, let's say some f dx2 wedge dx3, d eta is df dxi wedge dx2 wedge dx3. Remember? Basically it's df wedge dx2 wedge dx3. Does this ring a bell? I thought. It's the exterior derivative, remember, and d square is 0 and so on. Likewise, in Cn, if eta is, let's say, let's take a particularly nasty example, maybe not so nasty, I'll just block myself. Say we have this, there are two kinds of exterior derivatives. One is this, which is sum over I, del zi dzi wedge this. Another is del bar, which as you can imagine is del z bar dz bar wedge this, which is of course just z1 bar dz1 wedge, and in this case it's because this is z times z bar, of course, z1 dz1 bar. Okay? You have the del and the del bar exterior derivatives, which just means you take the del derivative of the coefficient or the del bar derivative. Okay? And you can also see, here is a very trivial exercise, it's not even an exercise, but yeah, just do it just for your practice. Prove that d eta is del eta plus del bar eta for all forms, for all k forms eta. Okay? Of course, and might as well when we are at it, and that del square and del bar square are 0. I'm making such a big fuss about this del square and del bar square being 0 because not only will we need it later on, if you ever grow big and strong and you hear the words almost complex structure, an almost complex structure defines a complex structure if and only if del bar square and del bar square is 0. You don't even need del 0. So this is differential forms in Rn and Cn. We will talk about them on manifolds as well. But for now, let's do something else. So now we can produce lots of examples of complex manifolds. For example, x square plus y square equals 1 in C2, or for example, right, say something like this, and this in C3. I'm defining it with the help of two equations. So how do you prove these are all complex manifolds? So for example, in this case, you take the derivatives of these functions, let's call this f and g, if you take del f del z and this, okay, this matrix has full rank. In other words, this and this are linearly independent. When restricted to the level set. So by the implicit function theorem, these are actually honest complex submanifolds. I hope these words make sense. I mean, I urge you to calculate these once at least so that you get some practice, but yeah. I hope this makes sense. So we can, of course, now you can see a pattern. You can produce lots of examples of complex manifolds. Now this is somewhat an ill-defined question, probably sounds stupid at first glance. Can you see a pattern in these two things? Is there something common? In the topology of these two things, is there something common? But those two examples, they are non-compact. How can you see that? You can probably try to see it directly. You can make one of these guys go to infinity, nothing's going to go wrong. You can still solve for one of the others in terms of this, not a problem. Yeah? These are non-compact. And this can be seen directly. A direct calculation shows you this. Now already things are beginning to look a little uncomfortable, right? How do you produce How do you produce examples of compact, smooth manifolds? You take a function, set it to 0, x squared plus y squared equals 1. But here, that same x squared plus y squared equals 1 is not compact. Maybe we have been bad in our choice of functions. Maybe if you choose 3 or 4 functions in a very clever manner, you can, through some ingenious conspiracy, they can become compact. But no, the answer is, unfortunately, if you wish, this is a theorem, there are no compact, complex submanifolds of Cn. This is actually not a theorem, this is a corollary of this theorem. Every holomorphic function f from M to C, where M is a compact, complex manifold, is a constant. By the way, what does a holomorphic function on a manifold mean? I haven't defined it, right?
Composing by the chart.
Yeah, in each local coordinate chart, it's an honest holomorphic function, right? And this notion does not depend on what chart you choose, thanks to the chain rule. Okay.
Connected also.
So the thing is,
Connected also.
sorry.
Connected.
Yeah, of course. So all manifolds are connected unless otherwise specified. Not equal, whatever. You know what I mean. Okay. Right. How is this a corollary of this theorem? Yeah. So if this was a submanifold, the coordinate functions Zn are holomorphic and they are constant, so you're in trouble, right? Okay, so we have to prove this theorem. Unfortunately, this requires a little bit of analysis, and I'm not going to wave my hands when I do that. You'll see soon that I'll wave my hands in several places. This is just a warm-up for you to get used to it. So, suppose, maybe sketch, if f equals u plus ib is such a function, okay, u is a function from M to R, M is compact, so U achieves its maximum at a point P. Okay? Now, notice that, which means that the gradient of U at P is 0, correct? Alright, now f is holomorphic. Choose coordinates z1 to zk, if you will. What does this mean? It means del bar f. Maybe I'll write it like this. It's just so that we get used to this formulation. Notice that I can package the Cauchy-Riemann equations in one go by saying that this 0-1 form is 0. I hope this is clear. Instead of saying df dz 1 bar is 0, df dz 2 bar is 0, and so on, I can say that d bar f, the 0, 1 form itself is 0. Exercise, prove that this means in local coordinates u is harmonic. That is d square u dxi square is 0 near p. So what is the problem? You have a harmonic function achieving a local maximum. I claim this is not possible. Harmonic functions cannot achieve local maximum. Okay? So how do you prove such a thing? Well, that requires some work. Let's see if there's a very quick way of saying that. Yeah. Any one of those things will require the mean value property, which I don't want to go into. But you can imagine that this is the case, right? At least in 2 dimensions, I hope you know this, the maximum principle. I don't know what they teach in analysis. But anyway.
Actually, this is an economic statement, right? Every harmonic function is real part of some harmonic function.
So that's true in one way.
One dimension.
Yeah.
So it's not true.
Well, that's a good question, and it's not. Ignore this if you don't want to think about it. But if a function is pluriharmonic, what is this? This is a 0-2 form. If this is true, then you're right. U is indeed the real part of a holomorphic function by optional exercise, if you wish. Oh, sorry. 1, 1. If this is the case and U is real valued on Cn, U in Cn to R, then U is the real part of a holomorphic function. This has a name, as I said, it's called pluriharmonic. And a pluriharmonic is obviously harmonic. If all the components of a form are 0, then you just add them up, the traces to the plus.
So,
Yes.
for that, if it attains maximum, local maximum, then I think by using derivative test we can prove that it should be constant.
No, that will only say that the second derivative is less than or equal to 0.
Because for subharmonic, I think we can do without using maximum.
If it is strictly, yeah.
Okay.
But if it's not strictly so, then it's a problem. See, the point is, if a function attains a maximum at a point, you take the second derivative matrix, it has to be negative definite, semi-definite. The problem is it can be semi-definite, it can be 0 also, that's not forbidden. That is what underlies the proof of it, but it's a little more complicated.
But if it is 0, then I think we can translate or something and make it strictly 0.
Yeah. That requires some argument. It requires some effort. One way is to add epsilon to it and make it positive, but you have to prove something else and so on. Another way is to prove the mean value property. Anyway, let's take this on faith. Okay.
The mean value property for polydisks follows from the one variable case.
Right.
So that's easy.
Sure. But even the one variable case, I don't know if people know it.
That's Cauchy integral.
Okay, fine. Sure. So, to recap, what we have done is we have defined a complex manifold and we have produced lots of examples of it by taking a bunch of functions, putting them to 0 and Cn. But unfortunately, we have proven that there is no way to produce compact complex submanifolds of Cn. So here's a question. How does one come up with examples of compact complex manifolds? Now, of course, before asking this question, the correct question to ask is why should we care? notice the reason I gave you for caring about this in the first place is to consider, say, things like conic sections and so on, like putting a bunch of polynomials to 0 in Cn, that gave you nice examples of these. So we wanted to study these in general. So is there a reason to even care about this? There is, but unfortunately that would be giving half of the answer away. Okay, so that's why I don't want to tell you why to care about this question right now. Okay? Before doing this, in smooth manifolds, what other ways do you know of coming up with examples of smooth manifolds? One is submanifolds of Rn. Unfortunately, every manifold is a submanifold of Rn, but ignore that fact. Concretely, how do you know how to construct examples of smooth manifolds? Other than putting a bunch of functions to 0. Yeah, that's a smart-ass answer. I mean, that's not what I'm looking for. Because that's not going to help us in our case, right? Because you don't have even one example of complex manifold. That's a problem.
Quotient
If you have a nice enough Lie
Excellent,
group
that's the
action.
point. So, what else is there?
Yeah, it's a nice enough Lie group action produces.
Fair enough. But in general, the philosophy, you're absolutely right. That it falls under the philosophy of quotienting, right? What's the simplest example of a quotient we know? We know the torus, right? How do we get it? We take a lattice, let's say E1 and E2 form a basis in R2, and let this be the set of all integral linear combinations of this. And you take this, then you get a torus, right? If you wish, the picture would look like, for example, something like this. And so on, basically. Right? So the same thing can be done here. Examples. One is a torus, a complex torus. It's just quotiented out by P goes to P plus N1 P1. Where these are all integers and EI form a basis. Okay. This is diffeomorphic to S1 cross S1 exercise, and this I expect you to do it for homework, if you will, rather than discuss this. Prove that this is a complex manifold. It is of course compact.
Shouldn't Ni come from Zi?
Z integers.
But then this would not become a compact thing.
Sorry, what I mean is E2n. This is an R basis of R. Okay, so okay. So exercise proof that there's a complex manifold. In other words, exhibit explicit coordinate charts. I urge you to do it at least once. For the next one, maybe we'll actually do it because it's important. What other examples do we know of in real ones? Like the torus is one example for quotient. Sure, you can take Lie groups and so on, but projective space, right? What do we have there? We have RPN. The problem is in real Sn quotiented out by something. I don't like this definition. This is not what we will use. You have something called Cpn. As a set, this is all complex one-dimensional vector spaces, that is lines passing through the origin. As a set, this is what it is. So what is it as a set? It means, so how do you produce a complex line? You just give me a vector, all vectors proportional to that. So all non-zero vectors, of course, you have to throw out the origin. And you identify two vectors when they lie on the same line, meaning when x naught is lambda x naught, where lambda is in C star. By C star, I mean C minus 0. Okay? So as a set, this is what it is. Claim this is a compact complex manifold.
I mean, you can define it by that sphere definition, by quotienting by U1. It is easy
Sure,
to see
sure.
this compact. then.
Sure. I'm coming there. Right. Okay. Fine. But that won't give you the complex stuff. Okay. So why is it compact? I wanted to give you as an exercise, but okay, he has already suggested this part. How do you prove it's compact? It's diffeomorphic to a very familiar kind of an object. Just like Rpn is Sn quotiented out by p to minus p. This is also the sphere quotiented out by something. It's S2n plus 1 quotiented out by S1, if you wish U1, whatever, same thing. Right, S1. So what does this mean? So how can you specify a line? One way is to tell me a vector and every vector proportional to it. Another is give me a unit vector, right? That will give me a line, except that if you take a complex unit vector and multiply by e raised to I theta, you still get a complex unit vector. So you're supposed to you're supposed to identify all of them. Okay? So as sets, these two are the same. You can prove that as smooth manifolds they're the same. But it doesn't matter. I mean, the topology is induced that way, so this is compact. Okay, so it is compact. That part is clear. The question is, why is it a complex manifold? If you want it to be a complex manifold, you better exhibit coordinate charts, right? I originally thought of leaving it as an exercise, but this is an important thing. These coordinate charts are somewhat standard, so we'll do them. Yeah. Okay, so how do you come up with coordinate charts here? Any ideas? How would you do this? Right. So the idea is the following. Naively, how can you identify a representative of this? If you're allowed to scale by any complex number, just pull this one out, right, for example. Except this makes sense not everywhere, makes sense on the open set U0 where x0 is not 0. Right? So let's call these coordinates Z1, except I'm going to do something a little unsavory. I'm going to put a comma and put a 0 here. Don't think this is a partial derivative. The reason I'm doing it is because I want to remind us as to what is non-zero, here x naught. Right? For example, if you consider the open set U1 where x1 is non-zero, so is equivalent to a standard thing like x naught, x1, 1 and so on, which I will denote as z1 with a 1 and so on. Okay? This second number indicates what is non-zero. Okay? So on, this is not good enough. This is merely telling us that on U0, this manifold is homeomorphic to Cn. We need to prove that on the intersection, for example, what is the change of transition change of this thing? How do you get this from this? It's a function of these guys, and what is it? How can I express these coordinates in terms of these? In particular, yeah. So for example, what is this? A function of these things. And what function is it?
Z2 upon Z1 1.
Right, so Z1 not, okay, is what? It's x1 over x naught. This one is x naught over x1, so it's just this. And likewise, whatever, that is x2 over x naught, and this one is x2 over x1, so it's just z2 naught over z11. And so on. All of these are of course holomorphic functions because this is non-zero and you can divide by non-zero holomorphic functions to get holomorphic things, right? These are all biholomorphism. This is a biholomorphism. And the same argument applies even if it's not U0 and U1 and something else. So indeed, this is an honest, complex manifold. We've explicitly produced coordinate charts, and it is compact because it is diffeomorphic to S2n plus 1 quotient S1. Okay. By the way, since this is not just an aberration, this phenomenon happens in general. I won't tell you what I'm talking about in great detail. What you're doing abstractly is you're taking Cn, throwing away a bad point, namely the origin, and quotienting out by something, right? And that surprisingly was equal to the same thing as some subset of Cn, namely the sphere, quotiented out by some other thing, by a real version of the thing you've quotiented out. You've quotiented this out by C star, this by S1. C star is the complexification of S1, right? So this is a general phenomenon. This is not a very special situation. In case you ever want to look it up, it has a name. It's the Kempf-Ness theorem. This, of course, involves more words than you will know. Broadly speaking, it's a subject called geometric invariant theory. Okay. Anyway, I'm just saying that this is a deep kind of a thing. So we have two examples of compact complex manifolds. But how do you produce more? If I give you one example, sure, as someone over there suggested, you can take products of these. That's valid. How else do you produce examples of manifolds? If I give you one example, you can try to produce submanifolds, right? If I give you a compact complex manifold, ideally, if life was good, you would take a bunch of functions on this compact complex manifold, a bunch of holomorphic functions, set them to 0, and you should get a submanifold. The problem is there are no non-trivial holomorphic functions. So we seem to be in a fix. The hope is to produce compact complex submanifolds of any of these. But we can't set a bunch of holomorphic functions to 0 because they're all trivial. Okay? In fact, our hope is a little bit more. Remember our original question? In this case would be, is every complex manifold by a submanifold of some standard one, of a standard one. Not just any old submanifold, by the way, a closed submanifold as a closed subset. This was our original question. The answer to this is no, right? I mean, it's not still obvious that it is no. At least Cn does not work because compact complex ones cannot sit in Cn. So a modified question would be, is every compact complex manifold, say for example a submanifold of projective space? Here is a slightly more plausible question. More plausible. Is every, or the torus, but let's look at the projective spaces. Seems unlikely it's the torus, that's too special. Compact complex manifold is submanifold of CPM. First of all, are there submanifolds of CPM? Forget this. 0th question. Are there any submanifolds? Are there any non-trivial complex submanifolds of CPM? Right? So these are interesting questions, and I'll give you the answer to the first question. The key phrase is the Kodaira embedding theorem. It says that if so and so happens, then your manifold is a submanifold of CPM. And in fact, if you take a random complex torus, if you throw a dart at the space of complex tori, with high probability you will hit one that is not a submanifold of CPM. The answer to this is no. Counter examples. Any torus, not most tori, complex tori. They are not. By the way, these things have a name. If you are a submanifold of CPM, this is called a projective manifold. Okay. So, if you choose a complex torus at random, you're certainly, almost surely not going to be projective. Okay? So yeah, so our dream of embedding everything in a standard thing will not work. In fact, you can ask another question. Okay, is every non-compact complex manifold a submanifold of Cn? That seems more reasonable, right? That's also false. It better be a special kind of a non-compact complex manifold. It's called a Stein manifold. Okay? So the Kodaira embedding theorem tells you the answer to this question. Embedding theorem. Very abstractly, it says if a differential geometric condition holds, then indeed it is the case. But how do you check whether that condition holds? That's a different question. Okay? So this is the aim of this set of lectures, to at least state it, if not give an idea of the proof. Okay? Alright, so the 0th question. how does one produce examples of submanifolds if you can't set a bunch of functions to 0? Let's see. So let me write this for the record. The answer is no, even for non-compact sitting in Cn. Okay. Okay. All right. So as I said, you don't have, you can't set a bunch of functions to 0. But here is something you can try doing, right? After all, what is CPN? CPN is basically Cn plus 1, except that you're identifying a bunch of things, right? So here is the first attempt. Naive attempt. Take, let's say, one function. Let's say some holomorphic function on Cn plus 1 and set it to 0. Okay? Does this give you, after quotienting, a submanifold, a well-defined thing? This is holomorphic. Well-defined. In fact, why holomorphic? Let's take a polynomial. Well-defined object in CPU. Okay. So that's the most naive thing to do, right? Why don't we just try to take x0 square plus x1 square equals 1? Right? The problem is, supposedly, if you take lambda x0 and lambda x1, they're the same point in CPN, right? But this is lambda square, which is not 1. So that's completely false. So our naive attempt is not correct. Second attempt. Where is this going wrong? Instead of x0 square plus x1 square equals 1, I'm getting a lambda square. So to cancel it out, what if I try something like this? This seems to define a well-defined object inside CPU. Right? At least it makes sense, the 0 locus. Is this a I mean, of course it will be compact, that's not rocket science, more fundamental than that. But is it a complex submanifold? Right? That's the question. More generally, suppose F is a homogeneous degree D polynomial with complex coefficients. That is, F of this equals lambda raised to D times this. Then F f of x naught is 0 is well defined on CPN, because if y naught yn is equivalent to x naught to xn, that is, it's lambda times this, f of y naught to yn, as long as this is not 0, is equal to 0 if and only if f of x naught to xn is 0. Right? By the way, from now on, the set of things equivalent, the set in Cn plus 1 equivalent to, should have written, the equivalence class will be denoted by this symbol with the colon, and these things are given a very confusing name. They're called the homogeneous coordinates. Coordinates. They are not coordinates in any sense, but they're just given that name. Okay. Right. So this is a well-defined thing, and the point here is the following. Proposition, if you will. If df dx naught, df dx1, df dxn is non-zero on f inverse 0, then f inverse 0 defines a compact complex submanifold of CPN of dimension, compact complex n minus 1 complex dimensional submanifold. Okay? So how would you prove this? Sorry? Not quite. Well, they are, I mean, that's fine, but how does that help? By the way, before I forget, it's a hard result due to say that every compact complex submanifold of CPN arises as the simultaneous zero set of a certain number of homogeneous polynomials. Okay. It's an extremely non-trivial result. Maybe I'll just mention it before I forget it. And it's called, in his paper, his famous paper, Geometry Analytic, Geometry Algebraic, that every compact complex submanifold of CPN is the simultaneous zero set of a bunch of homogeneous polynomials. If you want to see a proof of this, perhaps a modern proof that's not written in French, that's in Griffiths and Harris. That's also a terrible book, but it's the best we have, unfortunately. Yeah, I suppose, but that's too algebraic for my taste. Lindenhill, yeah? Is there a bound on the number of homogeneous polynomials? Can you explicitly calculate that somehow through Chern classes or some such nonsense? No. There must be. Who cares, right? Yeah. But yeah, so anyway, so how does one go about proving this? I mean, obviously one has to use the implicit function theorem, the complex version, but more concretely, how does one do it? I agree it's just a calculation, but we better do it. Okay, so let me do this. So the point is the following. So on u naught, that is x naught is 0, assume that df dxj, sorry, maybe I should write it as capital F. I don't know. Is not 0 by assumption, by hypothesis, right? It's for some j. Right. Now, suppose you take zi is xi over x naught. So f of z1 to zn given by 1 z1 zn is 0. So df dzj is df dxj, which is not 0. Okay? So by the implicit function theorem, we are done. Except for a very small point. What is that point? This seems to be missing one small thing. Yeah. Suppose if we got unlucky and j is 0 and all the other guys are 0, then you can't use the implicit function theorem. This is impossible. And I leave that to you as an exercise. Why? Just think about it. And these things are not deep. All I'm saying is I'm using the implicit function theorem. I just have to choose coordinates properly, which I have already done so. Okay. You just have to be a little nitpicky about these things. It's not very difficult to do. Okay. I hope this is clear. All right. So in other words, so So now we have lots of examples of compact complex manifolds. So you take sum of ai xi is 0 where sum aj is non-zero. This is a homogeneous degree 1 polynomial, right? Polynomial. And this is given a name, it's called a hyperplane. Why? Because on U0, for example, this is an actual plane in Cn. See, you should think of Cpn as almost being Cn, but with something at infinity, akin to your sphere in one dimension. Cp1 is just your sphere. Take C1 and add a point at infinity, right? So this is called a hyperplane because it's an actual plane in Cn, just that at infinity something happens. Okay? This is obviously from that proposition, it's a submanifold. Likewise, this proposition can be generalized to more than one function, one polynomial. More than one homogeneous polynomial. So in particular, x0 square, sum of xi square is 0 and sum of xi is 0 defines a complex submanifold of dimension n minus 2 in Cpn. Okay? Right, so now we have examples, but lest you be tempted to think that every complex submanifold, let's say of dimension d, is the simultaneous zeros of n minus d homogeneous polynomials, that is false. To get, let's say, a two-dimensional, this is just a coincidence. I'm saying if you want this sort of a thing, you might have to use 5 functions. Maybe 2 functions may not suffice. Okay? It's just a coincidence.
So is the obstruction for getting a complex manifold to be a submanifold of CPN some restriction on the normal bundle?
Submanifold.
I mean, you take an arbitrary manifold and you try complex manifold and try to embed it in CPN. Is the obstruction some structure on the normal bundle of that?
Well, how would you embed it? That's the whole problem,
Oh, I
right?
see. Sorry. I think there maybe there's something, some restriction on the tangent bundle, like.
It's not it is an obstruction, but we'll get to it. It's more subtle than you think. Okay. Okay. So now we have lots of examples of these projective manifolds. So while we are on the subject, just one more piece of terminology. A bunch of homogeneous polynomials set to 0 is called a projective variety. It's a manifold if this sort of a condition holds. Okay? Otherwise, it's not necessarily a manifold. And you remember I asked you why you should care about compact complex manifolds? Because these projective varieties are very natural in algebraic geometry. Why are they natural in algebraic geometry? Here's the reason. Suppose you want to make a statement like, this is a silly question. How many points do 2 lines intersect? Complex lines, not just real. You will say it's 1, except if they're parallel, then you're in trouble, right? But if you allow points at infinity, 2 parallel lines intersect at infinity, right? So if you allow infinity, this question always has an answer of 1, except when they coincide. That's an even more subtle question, but pretend that's not the case. More generally, if I ask how many points do 2 things intersect, well, let's say 2 conics, how many points? the answer should not depend on whether there's an infinity or not. That's why you do algebraic geometry on projective varieties. Now, of course, the question of what happens when two things coincide, that's a more subtle question. That's where scheme theory comes in. But yeah, so that is the point. You care about compact complex manifolds because a lot of them are projective varieties, and you care about projective varieties for a different reason. Okay. Okay. All right. So now all of this is nice and dandy, except we are in. This was a very ad hoc construction, right? Remember I said, okay, let's try one naive attempt, another naive attempt. Maybe I'm being too naive and stupid. Maybe someone intelligent can do it better, right? That's not the point here. That is the point, but there's a different point here. That x0 squared plus x1 squared equals 0 defines a submanifold of CPN, right? But x0 squared, f equals x0 squared plus x1 squared, is not a function on CPN, from CPN to C. Ideally, we would want to say that we want to produce submanifolds by setting a bunch of functions to 0. Except that this is not a function from CPN to C. So this is suggesting that maybe C is the wrong thing to use. Maybe x0 squared plus x1 squared is a function from CPN to another complex manifold. Now that seems plausible, right? We have not proven a theorem saying such functions are trivial. It depends on what complex manifold it is, right? So what is this? That's the question. Just, by the way, we will denote that complex manifold by a fancy name, script O2, but I'll come to that, okay? So how would you do this? How does one identify what that complex manifold ought to be? Maybe this is too complicated a function. Let's take just the function f of x0 x1 dot 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 as simply equal to x1. This is also not a function to C, right? Just the function x1. Let's try to identify what it is a function to. So if f is a holomorphic function to some manifold, then locally, if you take the coordinate on u0, which is x0 is non-zero, x1 corresponds to the coordinate z1. After all, x1 equals x1 over x0 z0, which is z1 times x0, correct? If this was an honest function to somewhere, then locally its representation should be f of z1, z2, so on equals z1, right? This is reasonable. Now, on let's say we take another coordinate chart. On another coordinate chart, let's say uj is non-zero, xj is non-zero, x1 is some w1 times xj, which is x1 over xj times xj. See, what am I trying to do here? If this was a function to complex numbers, regardless of what coordinate I choose, I should get the same thing. But here I'm not. Right? So if I choose a different coordinate chart, x1 seems to correspond to a different function, to w1, which is not z1. Right? So what will we do now? We will do what mathematicians usually do. You just pretend that they are both the same. In other words, w1 is not the same as z1, but this is the case, right? So morally speaking, x is f is not a map from x to c, but is instead a map from x, have I been calling this x or m? M to c. From m to this weird space. I'll just make this clear in a moment. As of now it sounds scary. This is a strange object. So what am I doing here? Okay. So this function is not a function to complex numbers, because when you change coordinates, it's not behaving properly. Right? So what I do is I'll force it to be a function to something. How am I constructing this something? I'm taking ui cross c. If I note that this thing z1 is a function from u0 to u0 cross c, right, given by p goes to p comma z1 of p. Correct? So I have a function to ui cross c's, except they don't agree, right? So on the overlap, they are related by means of multiplying by a holomorphic function called gij. I hope this is clear. On u0 I have a function which I will treat perversely, if you wish, as a function from u0 to u0 cross c. On u1 or uj I have a function to uj cross c. They don't agree, but they are related by simply multiplying by a holomorphic function that depends on ui and uj, of course, called gij, which is given by this explicit formula. Right? So this, if you know what vector bundles are, this is an example of a line bundle. So let me So this forces us to define these objects called vector bundles, or in this case line bundles. This manifold is in algebraic geometry, it's denoted in a fancy way with a script O and a 1. What the hell does this 1 stand for? I'll come to in a moment. Because it can be a 2 or a 3 also, but what do they mean? So this is, I'll write the name of this. It's called the hyperplane line bundle. Okay. And these things, x1 is a section what do these words mean? I'll come to them in a moment. If you already know what vector bundles are, then very quickly this is a holomorphic line bundle, and those are holomorphic functions. But if you don't, here is what it is. So this manifold O1 is a very, it's a curious object because it's not any old arbitrary thing. It has a nice structure to it. Notice it's formed out of taking cross products, right? UI cross C. So there is an obvious map from this to to CPN given by the equivalence class P comma V is equal to phi of P. Okay. This is a well-defined map. Before we show well-definedness and so on, here is an exercise. Prove that, actually, yeah, I have a bigger exercise to annoy you, so might as well just write that. Okay. There's an obvious map like this. Now, pi inverse of a point Q is what? If I take a point here, what are all the points on this manifold corresponding to it? Yeah, so if you take a point here, you have an entire complex plane sitting above it, right? So pi inverse Q is a one-dimensional complex vector space. So a complex line, if you so will. C. So O1 consists of a bunch of C's varying holomorphically on CPN. In other words, you should think of it as if this is CPN, O1 is a bunch of lines, right? This is O1. Right. So this is an example of a holomorphic line bundle. So let me define a line bundle in general and then connect it to the usual definition that you may have seen, some of you. Definition. A holomorphic line bundle L over a complex manifold M is L equals G alpha beta of P multiplied with B beta, where U alpha, union of U alpha is M, and these are open sets, and they are called trivializing open sets. Open sets. G alpha betas are functions from U alpha intersect U beta to non-zero complex numbers, holomorphic. Satisfying G alpha beta is G beta alpha inverse and G alpha beta G beta gamma equals 1. These are the so-called transition functions of L. So let me just go over the definition. What is it? A holomorphic line bundle over a complex manifold is this weird object, U alpha cross C. It's almost like M cross C, except it's not. It's U alpha cross C with an equivalence relation, where a vector from here is identified from some other vector here by means of a linear transformation that depends on the point, okay? And these are called trivializing open sets. These G alpha betas are holomorphic, that's why the adjective holomorphic line bundle. The line comes from the fact that it is C1, right? Satisfying these two conditions. These are sometimes called co-cycle conditions. But fancy terminology aside, it's just a holomorphic line bundle is simply a bunch of functions, G alpha betas. Right? Now, if you've already seen vector bundles, this is not the definition you might be familiar with. So let's be a little masochistic, and I will give you this exercise which we will discuss tomorrow. Prove that L is actually a complex manifold of dimension, of complex dimension, of dimension n plus 1, where n is the complex dimension of x, of that. Is it m or x? What? M. There exists a projection map pi from L to X, which is holomorphic, such that pi inverse of this is C. These vector spaces are called fibers. Okay. Pi inverse of P is called the fiber at P. Around every point P, there exists an open set U sub P such that pi inverse of U sub P is biholomorphic to U sub P cross C with the biholomorphism being linear on the fibers. In other words, let's say there is a map phi from here. Phi has to be compatible. So you have M, right? You have a map M here. You have pi, and let's say pi tilde. This diagram has to compute. And this phi is linear on the fibers. It's a linear transformation on the vector spaces. And optional, this is a little harder. Prove that every complex manifold L that satisfies the above is actually biholomorphic to a holomorphic line bundle with the biholomorphism being linear on the fibers. Okay. How many of you have seen vector bundles again? Can you raise your hands? Non-trivial number. So it's just saying that a line bundle in the usual sense is the line bundle in the sense I defined with the adjective holomorphic. Okay. Oh, and alright, so please do this exercise. We'll discuss it in the next lecture tomorrow. Notice that this object is forced upon us. We did not define it arbitrarily. We require this so that the homogeneous polynomials, at least of degree 1, are functions to this manifold. Okay? Okay. So some more generalities on these holomorphic line bundles. Most of you probably know these things, but still, the ones who don't. A holomorphic function S from X to L such that pi composed with S of P equals P, meaning X. So X and M are interchangeable for me. So L is simply this whole base. S is like a map taking P to S of P. From every point goes to the some vector on this vector space. Is called a section, a holomorphic section. Okay, and so for example, x0, x1, so on until xn are holomorphic sections of O1 over CP. Why? Well, we defined O1 so that this happens. We constructed O1 with the requirement that x1 better be a holomorphic section. I'll leave it to you as an exercise to prove that the other guys are also holomorphic sections. Any questions so far? Okay. One more piece of terminology. We say that S from an open set in M to C provides a local trivialization for L over U if S of P is not 0 for all P in U. Okay? note that P S can be used to construct a biholomorphism from pi inverse U to U cross C. Namely, if you take P comma V goes to P comma V divided by S.
So that
This
S
is-
maps into X, right? The target of S in the first line. Because you can construct a constant function.
Sorry. What's this called? What did I call this? L.
Yeah, L. Yes.
So, yeah, you're right. By the way, U is an open set. This is not. So it's not because it's a constant. Yeah. So, okay. Sorry. Sorry, I didn't. SP is not 0 in the sense that S of P is actually equal to P comma some vector V, right? This vector is not. Okay? Yeah, thanks. That's a good point. Okay, so this is called a local trivialization. So in other words, every vector is something times this. That's my point. Okay? Okay. Right. So other than O1 on CPN, what examples of holomorphic line bundles can we have? Now this is a very non-trivial question, but we just want a few examples. A stupid example is this one. Just take CPN cross C. In fact, any manifold n cross C. This is the so-called trivial line bundle, rightly so. 0th example. But here are more complicated line bundles, and we will need these constructions soon. Okay. Construction of new line bundles from old ones, from two given ones, V and W. So how do you construct two vector space if you're given two vector spaces, right? One-dimensional vector spaces. Well, one way is to take the tensor product. One way is to take the dual, for example. You can apply the same operations here. So V star, called the dual line bundle, is a bundle whose fibers are duals of V and whose transition functions G alpha beta tilde is just the inverse of this. What is a line bundle for us? It's simply a collection of transition functions. So if you just invert them, they will still satisfy G alpha beta equals G beta alpha inverse, and G alpha beta G beta gamma G gamma alpha is 1, right? So you get a new set of transition functions. They correspond to the dual. Okay? V tensor W is a line bundle whose fibers are Vp tensor Wp, and the transition functions are simply G alpha beta times H alpha beta. This guy has G alpha beta and this H alpha. Okay? So it's just the product of these two complex valued functions. Lastly, suppose F from N to M is a holomorphic map then F star B, called the pullback, is a line bundle over N with transition functions F star G alpha beta defined as G alpha beta composed with F. So what does this mean? If you have a map to another complex manifold, right, that thing has a line bundle over it. So what you do is create a line bundle here by simply defining the transition functions as take a point here, throw it there and use the transition functions there. That's the most obvious thing you can do. That's what you've done. Okay. For example, if N is a submanifold of M, with I being the inclusion map, I star B is called the restriction of V to N. So if you have a submanifold, you can restrict the line bundle to get a new bundle on the submanifold. Okay. All right. See, the O1 line bundle I have defined was forced upon us, but actually topologists like some other line bundle, which is forced upon them for another reason. That's the dual of O1, and that has a very pleasant geometric definition. The dual O1 star is written as O minus 1. Why? Because O1 tensor O1 star has trivial transition functions. So this is actually the same as CPN cross C, the trivial bundle. That's why the minus. It has the following nice, it's called the tautological line bundle. And its definition is the following. You can define it two ways, as the dual of O1 as we defined, or we can first define this guy and define O1 as the dual of this. Okay? So the space L, a subset of CPN cross Cn plus 1, consisting of, and this is a little easier to understand, I suppose, comma V0, V1, Vn, this is V vector, such that V is mu times x for some mu in C. Okay? The projection map is simply this. Okay? Can anyone tell me what the geometric meaning of this is? CPN is the space of all lines as a set. So as a set, what is this? How am I getting a vector space over every point on this set? It's the line, right? You take the space of all lines, take the line corresponding to. So that is this thing. which we will denote as O minus 1. Right? So alternatively, the hyperplane line bundle is the dual of this. Right? Why is this thing called O1? What would O2 be, or O3 for example? Any guesses? Where is the 1 coming from? Yep. So the thing is, suppose I take O1 tensor O1. What are its transition functions? That's G alpha beta times G alpha beta, which is G alpha beta squared. Okay? In general, O minus 1 has transition functions G alpha beta raised to minus 1. So OK has transition functions G alpha beta raised to K. If K is positive, K times. Okay? So what's the point of defining that? So why did we define O1? Because homogeneous degree 1 polynomials are sections of O1. What should sections of OK be? Homogeneous degree k polynomials. So for example, x0 square plus x1 square is a section of O2. In general, degree d homogeneous polynomials are sections of OD. Exercise. Verify this.
Sir,
Yeah?
are there some good sections for O minus?
That's an excellent question. There are none. That's a very good question. What about O minus 1? There are no non-zero sections. There's an obvious section, the zero section, but nothing else. Okay? It is actually hard to decide when you have holomorphic sections or not. Okay? So it's not a trivial problem. In fact, the Kodaira embedding theorem, since we are already at this point, I can say, roughly it says that if you have a holomorphic line bundle with lots of sections, then you are a projective manifold. But what does lots of sections mean? How many sections do you need? We'll discuss that. And how does one verify this? It seems like a very hard thing, right? Constructing this line bundle itself took us so much effort. How do you verify that you have some bundle having lots of sections? Clearly that's not the right way to go about things. So you need a differential geometric criterion we will provide. So here's a theorem, and this is a very, the theorem itself is not mind-bogglingly difficult to prove, but it's a very deep result. This is what underlies the relationship between complex geometry and algebraic geometry. Every holomorphic section S from CPN to O1 is a homogeneous degree 1 polynomial. In other words, sections are to be thought of as generalizations of functions to complex numbers. This is in some sense saying that in a sense, all functions come from algebra, namely polynomials. This already hints that every complex submanifold is probably algebraic, as if it comes from polynomials, right? So, how does one prove this? I do it tomorrow. Probably. Okay, start. Maybe let's see. Do this. Okay, suppose S is a section of this. Okay? So, what does that even mean? Okay. Think of O1 as the dual of the tautological line bundle O minus 1, which I erased. This is a subset of this, remember? Okay. So what does this mean? This means that at a point x0, x1, so on until xn, this thing, which is equal to this point, comma a vector, remember, comma a vector w, where w is a linear functional on O minus 1 at that point. What's the meaning of dual? It just means that you take a vector. It's something that takes a vector and spits out a number, right? And does so in a linear manner. i.e., define a function from Cpn cross Cn plus 1 like this. X b0 bn, this subset O minus 1 from this as S of x0 x1 acting on so we have a function on a subset of Cpn cross Cn plus 1 defined like this, right? Okay. So this f, let's see. So since v is mu times x, f, we can define another function, f tilde, from Cn plus 1 minus 0 such that f tilde, rather, let me write it this way. You can think of f as a function from Cn plus 1 minus 0 satisfying function f tilde of lambda x naught x is lambda times this. Why? What am I trying to say here? What does this mean? What is this function f tilde? What I'm saying is, you take a point and you give me a complex number, which tells me how much I have to mark. You take a point and you take a vector and it gives you a number, right? But this vector is not some arbitrary thing. It's just, if you wish, if you fix x0 to xn, you just multiply that by mu to get this vector, right? What does it mean to be a linear functional? It means if I multiply this guy with mu, if I multiply this thing with something, it pulls out. You need to think about it a little bit. Do people understand this? Given a linear functional on O minus 1, namely, given a function on this subset of Cpn cross Cn plus 1 that looks like this, that is linear in this variable, I claim I can find a function from Cn plus 1 minus 0 to complex numbers satisfying this. Okay, let's say you believe me. So in other words, I have a function from Cn plus 1 minus 0 satisfying something. Okay. And here comes the main point. It's holomorphic. By Hartog, f extends uniquely from Cn plus 1 to C. Like in chess, this is the key move here. Okay? df dxi are homogeneous of degree 0. Implies f is a constant, implies that df dxi are constants. So f is y. Degree 0 from Cn plus 1 to 0 to C equal to their values at the origin.